pick a particular structure and network structure. And for example, this is called fully connected, the simplest one, vanilla version. And you pick a loss function and you just pick a classifier, optimizer, which is one of those kind of a gradient descent algorithm. On my I showed you how to do, for example, the fetching MNIST I mentioned last time, but let's just count some of the parameters so we know the model better. So for this particular data, we have 60,000 observations. Every observation is actually an image, 28 by 28, and it's a gray color image, so there's no channels, only black and white. So the data is sort of stored in a 28 by 28 matrix, and then we're going to actually just put them as a huge vector. So that'll be our input. We have 10 classes, and the name is from 0 to 9, and here are the actual text and the name in English for the 10 classes. And we can actually take a look at what the picture look like. Okay, so here's how we're going to do the pre-processing. Usually the number is from 0 to 255, so you scale them to be just between 0 and 1. So let's set up the network structure, and the grammar is actually very simple. So you're going to get into some kind of a stage like the XGBoost or random forest, meaning this is built up on some complicated algorithm, but you don't need to know every little bit detail. You just use the package. So here how we specify the model layer by layer. And first you're going to do this sequential one, meaning move forward. First you're going to say, well, my input layer, basically you take your matrix, flatten them as a vector. So the input shape is 28 by 28, that's the input, but I'm going to flatten them as a vector. So it's going to be the dimensions, number of input is dimensions 28 by 28. And then we're going to build one hidden layer with 128 hidden nodes, and then output layer is 10. Once we get the numerical output, we do the so-called soft max, meaning e to the power that number and normalize it, we get probability. So this is actually a model with only one hidden layer. So once you do this, you specify the model. You also pick an optimizer, pick a loss function, because this is a classification. And we do sparse and categorical entropy, cross entropy, because our response variable is an integer taking 10 different values. And we choose our metric is accuracy. So here's a summary of your model. Now this is the input layer. The 784 is basically 28 by 28. Okay, so that's your input layer. And then you're going to go through a hidden layer with 128. Your input layer. So those are the number of nodes. There are 784, right? And then they're going to go to another hidden layer at 128. So it's fully connected. So there are edges between every pair from here to here. So how many parameters? For every hidden node, you're going to receive input as a linear function of them, plus an intercept. So for every hidden layer, you're going to fit a linear model with that many parameters, right? And you have how many hidden layers? 128. So that's the parameter go from the input to the first hidden layer. You can do the calculation, and that should equal to that. Makes sense, because we get a 5, first digit. We get an even number, so we're going to get a 0, right? Okay, so that's then you're going to get your output. From your 128 hidden layer, you're going to get output is 10. Again, fully connected. How many variables? You're going to have, for every output, is a linear function over this 128 inputs. Right, so you should have that many parameters. So this is sort of the structure. It's a very simple one. Okay, so you're going to specify the model, and then next just fit the model, and you take the model just call the command fit training X, training Y, and we're going to just loop our data 5 times because we do gradient descent. If you are running this on your own computer, then just call the first line. If you run it on a GPU, you want to do batch size because the whole idea of doing GPU is a lot of a redundant, simple calculation that can be, computed very quickly. So if you want to GPU, you want to gain that computation advantage, you want to use batch size, meaning every time you are processing not a single observation, but a small batch of them. So this data you can definitely run on your own laptop. It won't take long. And then you're going to take your fitted model, then you're going to do your evaluation. Train a test X, test Y, and you can look at the accuracy. The first one is log loss. Not bad because your project 4 is really 0.44, the lending club. And so the accuracy is about 87%. It's nice because as I mentioned before, if you are dealing with structured data, go with XGBoost or any linear model with regularization. But if you start moving to text data or unstructured data like images, you're going to find out this is very easy because you just use Lego blocks and you don't need to worry about pre-processing. Well, we did a pre-processing. We divided by 255. But overall, it's very easy to build a model. And we also checked, the accuracy, and you can take a look at the remaining output. So this is for the for this data, it's not exactly imagey because the picture, same as the MNIST data, the picture has been cropped and aligned up carefully. So a pixel here really means something. Like I can talk a pixel here. They mean something. They carry similar meaning. That's different from other type of image, which we'll get there later. So this is why when we're dealing with the image data, basically we just put them as a huge vector and use a forward network. Now, what about the movie review? That's a text data, right? So far for the movie review, I'm still going to treat it as, I'm going to talk about 2 approaches where you basically treat it as a vector. So for the movie review, this is same as your project 4. The data, let me show you what the data look like in this package. So if you look at the first training data, it looks like this. That means the data, so every integer, the integer can range from 1 to 10,000, I think, because that's the vocabulary size. So instead of putting the words here, just tell you the index of that word. So you can see, for example, some number will appear multiple times. So basically, this is a code word for each word. And the sentence stop here, we just add 0, just make sure all of them are the same length. Clear? So the data in this first approach, we're going to I show you some way you can actually kind of decode those numbers and find out the original text. Well, what we're going to do is, we have the data. The vocabulary size is 10,000, and we load the training data and training label, and they're just binary. Sentiment is positive or negative, and also the test data. And the data are basically in words, but it's stored in a way the actual English word is replaced by a number from 1 to 10,000, right? So there are 2 ways we can change this to a vector input. In the first approach, which is the approach we're going to use for your project 4, we basically do our one-hot encoding. We look at our vocabulary, which is a vector from 10 to a vector of length 10,000, and every entry will represent whether you see this word in this document or not. So it's binary. We didn't use frequency here. Make sense? So every document now represented by a binary vector of length 10,000. And if the binary vector, if a position is equal to 1, means that particular word has appeared in this particular review. So it's a huge high-dimensional vector. And so this is how we're going to do this pre-processing to get one hot encoding. The next thing, let's specify the network architecture. Let's start counting the parameters, right? So we have our input dimension now is 10,000, because that's from the feature. And what is the number of a hidden layer? We specify a hidden layer, we actually specify 2 hidden layers. The first hidden layer is 16. And we have another hidden layer is also 16. And then we output only one-dimensional output because of binary classification problem. And so let's see, when we go from the input to this layer, how many parameters we have? We have this number plus 1 times 16, right? Because for every hidden layer, it's going to calculate a linear function with 10,000 parameters plus an intercept. You have to do that 16 times. So this is why the number of parameters is going to be and this number. Okay? Then when we go from the first hidden layer to the second hidden layer, well, we have 16 to 16. So how many parameters? Is 16 plus 1, because that's a linear model this hidden node will receive, and we have to do that 16 times. Okay? So that's how you're going to get this number. And the remaining is just 17. Okay? Clear? Okay. And so you specify this is fully connected, use this binary feature and pick a loss function, binary cross entropy, pick an optimizer, and you can just start evaluating this. I actually generate this from using a GPU on Amazon, so I use my batch size. And you can now evaluate your prediction. And here the AUC is not one of the built-in metrics. You have to calculate by yourself. Here, so this, right, so the AUC. And where is the error? The ordinary classification error rate is not here. But well, we can compute by sum of those two and divide it by the total sample size. So you can compute that one. So this is one approach. And the second approach, which is based on the so-called embedding, and that if you look at the Kaggle website where we grab our movie review, they mention about this approach too. So the idea is they want to learn an embedding of every word in a particular latent space. They want to get some results like, suppose you embed stuff in a 2-dimensional space, and if this is a man, and this is a woman, and then somehow you could have king and queen. Somehow the difference is the same. This is all the idea of trying to do the embedding. Now, in short, what I mean is for a lot of unstructured data, image, text, the difficult part is we don't know how to represent those items. Okay, feature, that's the most difficult part. And so a lot of works focus on just getting the feature. It's called feature embedding. There are different ways you can do feature embedding. And a lot of, just check that Kaggle page, it will tell you different methods. One of them is actually using a one-layer neural network. But Keras can do this automatically for you. So what they're going to do is they're going to, first we'll only keep 256 words for each review. So if your review is too short, we're just going to add 0. If your review is too long, just chop them. We only keep the first 256 words. And then we're going to first learn our embedding. And meaning every word in my vocabulary, which is 10,000 words, they have to embed them into some kind of a feature space. And then that means for every review, you have a bunch of words. Every word corresponds to a vector. Then they apply some simple approach, basically just average the feature vector. So you get a number, and then you send into your neural network. So let's look at a summary of that network. You will understand. So our vocabulary size is 10,000. Here's how I specify my model. First layer is actually embedding layer. So we're going to, the input is 10,000, output is 16, meaning for every word in my vocabulary, I'm going to embed into in a latent space of dimension 16. Okay. So we have to first learn so every word going to embed into a space with 10,000, and then so that's what's the first. So for the embedding, let's look at what are the parameters, because you have to find out a mapping. 10,000 word, everyone corresponds to a 6-dimensional space. So that's the number of parameters we have to learn. Okay, and then as I mentioned before, you're gonna every review, which is every sample right now is a review that contains many words. Now it contains many 16-dimensional vectors. So you can do the so-called pooling by simple average, meaning for every review, now every review becomes a matrix of 256 columns. 16 columns, and for every review you have 256 words. Okay, so you just simply do a simple column average. So now that becomes your real input for your next layer of the neural network. So your input now, which is embedded feature, is going to be 16 dimensional. Right? So you have your. Then you're going to go with your. So this is it. This means the output from this layer, that means basically the dimension for the input for the next one. So if we have 16, once we do the average pooling, then this is going to be the input into a hidden layer of 16 hidden units, and then we're using the output. So let's compute, and you can compute the number of parameters. From here to here, it's going to be 17 times this. That's how many parameters. And from here to here, it's going to be 17, just because this is now the input for the outside for this output layer is a linear function plus the intercept, so 17. So this is all the those are all the parameters, and then you can just pick a loss function, and optimizer actually copy the same thing from my previous one-hot encoding and loss function optimizer, and you can just fit this. And then you can get your classification error and also your AUC. Okay, so a lot of them are not difficult to do, but of course we miss a very important part when we apply this approach. What's the important part? For text, definitely is the order matters. We basically ignore the order, right? So there's a family of, we won't be able to get to see in this time, but there's a family of neural networks are designed to model this kind of a sequential data. You could have the sequential data, meaning you give me somebody speak some sentence, you want to output something at the end, or there's a review and you want to output just one outcome, or you can think about somebody is speaking right now and you want to do translation. So you can output many things. Right after one word, you want to output something. And how we handle this kind of a hidden, when the order matters, again, hidden Markov model, right? So how we do hidden Markov model? When we do hidden Markov model, we have our X, we want to predict, but we feel like there's a hidden, something there's a hidden layer, which is the latent variable which you learned previously is also going to determine what you're going to get. And sometimes you can think about combine your supervised learning, which is the response Y, with a hidden Markov model. Meaning you're going to have an input from the hidden variable Z, not the hidden layer, but hidden variable Z, and you have the input which is from your feature X. So you sort of have this kind of two inputs. And the Z is always learned from the previous. I know it's quite general, but just want you to get a rough idea. And let's just take a look of how you're going to do this for this movie review data. I actually, you know what? I'll just show you summary model. I use this data. The same movie review data, and let's see. It's difficult to. Difficult to change this, but I hope you can read. So I load in the movie review data again, and we have our training and label. Now we use same as what we did before. We only focus on the first 256 words. Now if you don't have enough words, we're just going to add 0. Okay. Then we can run this so-called recurrent neural network. You can think about it's almost the same as the hidden Markov model. Oops. First, we're going to do our embedding. And now we're going to embed into a space with 32, not 16. So first is the embedding. We're still going to apply the embedding. So every word now corresponds to a vector in a dimension 32. And then we're going to do our simple recurrent neural network. So R and N with hidden units 32, and then just output. So let's count the number of parameters. The first embedding, of course, is the latent space 32 times the vocabulary size. So it's 320,000. Now, what is a recurrent neural network? That means you have your 32 input. You have your output is also 32. Input is also 32. But you have your another sort of hidden layer here. So this one's also 32. So for every hidden node, you're going to learn a linear function involving, which is going to receive an input not only from your feature X, but also from the hidden layer. Not hidden layer, but like a latent variable. And so the parameter is going to be 64, because that's the number of parameters, plus a location shift, which is an intercept, and times 32. Because for every hidden node, you're going to do this linear function. So that's what this parameter is. And then once you get to this outcome, and you just do your output on your prediction, which is one-dimensional because it's binary. Again, this is too simple for you to really understand and to that kind of a level, but I do want to show you the code so you can play with you maybe during the winter break. Play with this during the winter break. You can look at the result. Well, I cannot really show you the result, but you know what? Once I get home, I will create an HTML file. I'll show it so you can see how to apply this. You can use R and N. You can also use another one which is much more popular. It's called LSTM. So I think the LSTM accuracy is a little bit higher than the R and N. Of course, all those code I put there, you should try to use it as if you are playing Lego. I mean, you can always add a layer. You can always do something. But of course, a lot of tuning would be involved, which is sort of the unpleasant part of this. Okay, good.